Let's say we have 100 light bulbs instead of, well, let me actually just draw them. So I have one light bulb there. I have another light bulb. And I have 100 of them. 100 light bulbs. And what I'm going to do is, first I'm going to go, well, actually before I even start turning in these light bulbs on and off, let me let you know that they are all off. So they start off. They start off. Now, the next thing I'm going to do is I'm going to number the 100 light bulbs. I'm going to number them 1 through 100. So the first light bulb is light bulb 1. The second light bulb is light bulb 2, all the way to light bulb 100. And what I'm going to do is first, I'm going to go and I'm going to switch every light bulb that, essentially every light bulb. I'm going to go and I'm going to, so if I go, I'm going to switch, if they all start off, I'm going to turn them all on, right? So they'll all be, let me do it. So on my first pass, so let's call this pass 1. Pass. So on pass 1, I'm going to turn all of these on. On. They're all going to be turned on. And then in pass 2, what I'm going to do is I'm going to switch only every other light bulb. So for example, I'll say, okay, I won't switch light bulb 1. I'll only switch light bulb 2. So light bulb 1 will stay on. Light bulb 2 will be off. Light bulb 3 will be on. Light bulb 4 will be off. And so essentially every light bulb, if you look at their numbers, that is a multiple of 2 will be switched. So 100 will be switched, so that'll also be off. Then I'm going to come, and ignore this right here, and I'm going to switch every third light bulb. So what's going to happen? This one's going to, let me switch colors arbitrarily. This one's going to stay on. This one's going to stay off. And I'm going to switch the third light bulb. So this one was on. Now this one will be off. The fourth light bulb will stay off because I'm not touching it. The fifth light bulb will, what was it before? The fifth light bulb would have been on and it'll stay on. And now the sixth light bulb, in this case we switch it off and now it'll be on again. But I think you get the point. Every third light bulb, or if we look at the numbers of the light bulb, every numbered light bulb that is a multiple of 3 is going to be switched. And if it was a multiple of 3 and 2, it would have been switched on the first time and then off the second time. But I think you're getting the point. But what I'm going to do is I'm going to do 100 passes. So the first pass, I switch every light bulb. They all started off, so they're all going to be turned on. The second pass, I switch every other light bulb or every second light bulb. The third pass, I do every light bulb, every third one, or that's a multiple of 3. And my question to you is, after 100 passes, so after 100 passes, after 100 passes, after 100 passes, how many light bulbs are still on? Or how many are on, period? How many are on? And that is the brain teaser. How do you figure out of the 100 which ones are going to be on? And you should be able to do this in your head. You don't have to make like an Excel spreadsheet and actually do all the on and off switches. How do we know? So the first question is, how many of these are going to be on after I do 100 passes? And just to make it clear, what's the 100th pass going to be? Well, I'm only going to switch every 100th light bulb. So I'm only, whatever this light bulb is already doing, I'm just going to switch it. If it was off, it'll become on. If it was on, it'll become off. So the first question is, how many of these are going to be on after 100 passes? And then the bonus question is, which of these are going to be on? And so that's the question. Pause it if you don't want the answer, and then try to solve it. I think it shouldn't take you too much time. But now I'm going to give you the answer. Or maybe I'll start with a couple of hints. So we know, when do we know that a light bulb is being switched? So if I'm on the second pass, I will turn on, I don't want to say turn on, it might already be on. I will switch every light bulb that's divisible by 2. And then if I'm on the third pass, I'll switch every light bulb that's divisible by 3. So on every pass, what am I doing? Well, if I'm on pass n, and this is a hint if you want it. If I'm on pass n, what do I know? I know all the light bulbs that are numbered, where n is a factor of that light bulb, that will get switched, right? So we know that switched if n is a factor of the light bulb number. Light bulb number. And that's just a fancy way of saying, look, if I'm on pass 17, I'm going to switch all the multiples of 17. Or I could say, I know that I'm going to switch light bulb 51 because 17 is a factor of 51. So that tells you that we're always going to be switching one of these light bulbs on or off when one of its factors is our pass, right? So for example, if we're looking at light bulb, let me draw light bulb 8. This is light bulb 8. So when will it be switched? So on pass 1, we're definitely going to switch it on. So pass 1 is going to be switched on. Pass 2, it'll be switched off. I know that because 2 is divisible into 8. Pass 3 is nothing's going to happen. Pass 4, and pass 3, nothing's going to happen because this isn't a multiple of 3. Pass 4, what'll happen? It will be switched. It'll be switched back on. And then pass 8 is the next time we'll touch this light bulb and it'll be switched back off. So every time one of its factors go by, we're going to switch this thing. And as you can see, in order for it to be on at the end, you have to have an odd number of factors. So that's an interesting thing. So in order for a light bulb to be on, so for a light bulb to be on, has to have odd number of factors. Now that's an interesting question. What numbers have an odd number of factors? And this is something that I think they should teach you in grade school, and they never do. But it's a really interesting kind of number theory. It's a simple one, but it's interesting to think about. So what numbers are true? Let's do all the factors for some of the starting numbers. So all the factors of 1. Well, 1, the only factor is just 1. So 1 works. 1 has an odd number of factors. So that means that 1 will remain on because you're only going to turn it on in the first pass. Makes sense. 2. What are all the factors of 2? Well, you have 1 and 2. So 2, it has an even number. You're going to switch it on the first time and then off the second time, and then you're never going to touch it again. So this is going to stay off. 3, your factors are 1 and 3. 4, your factors are 1, 2, and 4. Interesting. Here we have 3 factors, right? We have an odd number of factors. So 4 is going to stay on. We're going to turn it on when our first pass. We're going to turn it off on our second pass. And we're going to turn it on again in our fourth pass. Let's keep going. So 5. The factors of 5 are 1 and 5. 6. The factors are 1, 2, 3, and 6. It's an even number, so it's going to be off when we're all done with it. 7. It's 1 and 7. 8, we just did that. It's 1, 2, 4, and 8. Still going to be off. 9. Let's see. 9, the factors are 1, 3, and 9. Interesting. Once again, we have an odd number of factors. So 9 is also going to be, the light bulb number 9 is also going to be on when everything's done. Let's keep going. And I don't know, maybe actually did this at our mental boot camp, and some of the kids, they immediately said, oh, well, the distance between 1 and 4 is 3, and the distance between 4 and 9 is, the distance between 4 and 9 is 5, and maybe the distance between 9 and the next number is going to be 7, right? It increases by odd numbers. And what's 9 plus 7? Let's just try that out. 16. What are the factors of 16? They're 1, 2, 4, 8, and 16. Interesting, that worked, right? From 9 to 16, you incremented by 7. From 4 to 9, you incremented by 5. So it seems like we have a pattern. But can you see something even more interesting about the numbers 1, 4, 9, and 16? You could try all the numbers between 9 and 16, and you'll see that they have an even number of factors. But what's interesting about all of these numbers? Why do they have an odd number of factors? In all of these other cases, every factor is paired with another number, right? 1 times 2 is 2. 1 times 6 is 6. 2 times 3 is 6. There's always a pair, except for these numbers. There's no pair, right? Why isn't there? 1 times 4 is 4, but 2 times 2 is also 4. So we only write the 2 once. 3 times 3 is 9. 4 times 4 is 16. So all of the lights that are going to be on are actually perfect squares. That's why they have an odd number of factors. So, what's our question? How many? So the question, this problem of what light bulbs are going to be on, boils down to how many perfect squares are there between 1 and 100. And if you could just list them out, and you could say, oh, well, that's just, the perfect squares are 1, 4, 9, 16, and you could try to think them all. Or you could say well, how many numbers can I square and get a number less than 100, or less than equal to 100? Well, 100 is equal to 10 squared. So you can only square the numbers between 1 and 10 to get a perfect square. So there's only 10 perfect squares between 1 and 100. Right? Hopefully you didn't lose that. But if that confuses you, just list them all out. You have to, given that hundreds is the largest number, it's the largest perfect square there, and that's 10 squared. The only other perfect squares in our range we're talking about are 1 squared, 2 squared, 3 squared, all the way up to 10 squared. And we could do that. 4 squared is 16, 5 squared is 25, 36, 49, 64, 81, and 100. So the numbers with the light bulbs with these numbers on it are the ones that will stay lit when we're all done. Anyway, hope you enjoyed that.